One of the tasks in the assignment for this session is to create a plot of the Fibonacci numbers and the ratios between consecutive Fibonacci numbers. So let's do something very similar. However, let us do the same thing for the Pell numbers. They are very closely related. It's a sequence of numbers, and a ratio between consecutive numbers approaches a fixed value, and that value is known in the literature as the silver ratio. So I'll start by opening a new script, saving it as, I don't know, Pell numbers, just to have some name for it. It's now saved on my desktop, and we want to now hide all those functionality up here to have more space on the screen. We need to define how many numbers do we want to see, and I start with setting n equal to 20, meaning I want to have 20 numbers. And we want to store our results in a vector called result, and we start by creating an empty vector which has the same size but only zeros in it. So I specify zeros with that zeros function, zeros, and I want to have a single row and as many columns as there are numbers, which is n. So now I have those sort of the result vector prepared. Now I need to specify the integers over which I want to calculate my numbers, in this case the Pell numbers. So I specify a range of integers which goes from 1 to n, meaning between 1 and 20 I will get all available integers. And that is my horizontal axis, which will then be used to display the Pell numbers. So one thing that we need to look up, sort of from, you can use Wikipedia or from the literature, is what are the first two Pell numbers, because like the Fibonacci numbers, you need to know the first two numbers in order to calculate the third. So when you look it up, it's fairly straightforward. The first Pell number needs to be equal to 0, and the second Pell number, which is in result the second position, so result in parentheses 2, is equal to 1. And I suppress any output with a semicolon at the end of the line. So after we have prepared everything, we can now run our for loop to create our results, and that is to fill in the corresponding values in the location of the result vector. So we do a for loop which runs from I equal 3 to n, and it calculates the result at the position I. Right? Do you see why it's 3? 3 is because first and second element have already been put in manually, so now the first thing to calculate is the third number. So the result I will be, and please look up the specific formula, but I'll just show you, it's 2 times the predecessor, so the number that is just before it in that array, which is called result I minus 1. And then we have to close the parentheses. So the new number will be calculated as 2 times the previous number plus the result at position I minus 2, the previous number, so the predecessor to the predecessor, so to speak. And you add those two up and create your result, and if that is all that you need to do, then end finishes the for loop. Okay, let's first see check if that for loop runs, and we can do this simply by typing the name of the result vector without a semicolon at the end. So it's marked It's highlighted in yellow because MATLAB wants you to know that you will see the output in the command window. But in this case, this is just what we want. So let's just do that. If I specify result, then I can see those 20 numbers that are now filled in, and that looks fairly good because those numbers are increasing at an increasingly big space. And those numbers are increasing at an increasing rate, reaching 6 million in the last number already. So what we can do, if we are happy with the for loop works with no error message, we can create our figure and plot the result as x, which are the numbers that we have specified, and the result, which are the result values that we have produced. And if you know how to specify whether you want markers or you want a line or you want a line and a marker, let's just do a line and a marker between the lines. So the line is specified by the dash and the marker, let's use the empty circle. -O in this case will show you that you want to see markers, but you want to have the marker connected with a linear line. And then because MATLAB's marker size is typically very small, so let's change that to a more reasonable value, which in this case I choose 20, and I think that looks fairly good. We can see the straight line which shows this exponential growth that gets steeper and steeper the higher you go in integers. And it also shows with marker size the actual points that we calculated and not a linear interpolation between them. Right, and finally I'll show you a trick how to see the logarithmic plot. So in the assignment it says make a logarithmic plot, and there's various ways to do it, and you can find out how to do it in code, but I want to show you how to do that interactively in the figure. And you can do so by going to View in that figure window and selecting Property Editor. And if that figure now opens in the Property Editor, you can pick which axis you want to change, and I want to change the y-axis or the vertical axis. So if I click on the y-axis, so I've selected it here, the y-axis, and then you can see that at the bottom it's maybe very small, but if you do it on your MATLAB it will be legible, that the y scale can be specified, and from a menu you have the option to choose either linear or logarithmic. So if you do that and you click logarithmic, then the plot will be automatically displaying the logarithm of the vertical axis. You can see it's then showing 10 to the 8, 10 to the 6, 10 to the 4, and so on, the logarithmic scale. And you can see that this semi-logarithmic display now changes the exponential function into a straight line. So that's how you identify it. If a plot shows a sharply growing curve, then you can try the logarithm, and if the logarithm turns it to a straight line, then you're probably dealing with an exponential rise.